Hello, and welcome to Radian and Degree Measure. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This is for Math 1508 Pre-Calculus at UTEP. Chapter 4, Trigonometry, comes to us from Larson's 10th edition calculus text, section 4.1, Radian and Degree Measure. So, what is trigonometry? Trigonometry, this is our first section of trigonometry in our pre-calculus class. And it's from the Greek, and it means measuring triangles. Trigono polygons, three-sided polygons. But before we can actually talk about the three angles of a triangle, what is an angle? Let's take a look. So an angle is determined by rotating a ray. So this is a ray. It's a half line, so it has a start, and then it continues forever in one direction. And we're going to rotate it about its endpoint. So we'll hold here, and we'll rotate the ray. The starting position we'll call the initial side. I almost slipped before I talked about it, and I called it its name. And the position after rotation, where it ends, is the terminal side. The endpoint of the ray is the vertex of the angle. So one way to look at an angle is an amount of rotation of a ray about its endpoint. A few more definitions. If we put the vertex of an angle at the origin of a standard Cartesian coordinate system, the initial side on the positive x-axis, then we call the angle in standard position. We rotate up if it's a positive angle, we rotate down for a negative angle. And so when we rotate up for a positive angle, remember the sun rises in the east and comes around and sets in the west. So a positive angle follows the motion of the sun, whereas a negative angle is clockwise. It follows the motions of the hands of a clock. Alright, so positive angle goes up and over, negative angle down and over. Still more definitions. We have a ton of them here. But when you start a new topic, it makes sense. For any angle, we can measure it in two different ways. We can measure both the positive rotation. In this case, this example, 120 degrees is their positive rotation. Or we could measure the negative rotation. Because an angle, we don't know. Did it start out with a positive rotation or start out with a negative 240 degree angle? And it turns out it doesn't matter. We call these coterminal. Coterminal because they share the same terminal side. Initial side is always on the positive x-axis, so that's a given. But they are coterminal if they share the same terminal side. How do we measure angles? Well, the measure of an angle is determined by the amount of rotation from the initial side to the terminal side. And we measure angles in two different ways. One is through radians and one is through degrees. And degrees, we kind of get, there's 360 degrees in a circle, and we'll talk about that a little bit later in this lecture. But what is a radian? And it's important for you to know that a radian is a real number, just like 4 is a real number. Whatever a radian is, it's a real number value. It's something we can actually measure. So 1 radian is the measure of a central angle theta that intercepts an arc length s equal and linked to the radius of the circle. Notice radian, radius, very, very similar terms here, and it's because 1 radian is when the radius is equal to the arc length. So if this was not an arc, it was a standard triangle, it would be like an equilateral triangle. All the sides are the same length, but this side just happens to be curved. Algebraically, it means that theta is equal to s over r, where theta is in radians. So arc length divided by the radius is equal to radians. Now we know the circumference of a circle is 2 pi r units, where r is the radius of the circle. We've known this since, I think, elementary school. Maybe we do geometry. It follows that 1 full revolution, starting at the initial side, coming 1 full distance around, corresponds to an arc length of s equals 2 pi r. And when the radius is 1, it's s equals 2 pi. So we have our coordinate system. Initial side, always positive x-axis. This is an angle of 0. I have not rotated at all. Pi over 2. Pi is half a circle. 3 pi over 2, and then 2 pi will get me back to the full rotation. We still have a quadrant 1, quadrant 2, quadrant 3, and quadrant 4, measured as we rotate through positive angles. Now we'll also use degrees on occasion, so know the degrees and the radians, but the radians are most important for our calculations. Alright, positive angles go up, negative angles go down. Kind of our whole system right here. So let's find some angles that are coterminal. A 90-degree angle. Well, first I'm going to draw the angle in standard position. A 90-degree angle is right here. Coterminal, so I want to measure the other way around, so I'm going to go backwards. But I want 90 less 360, right? Because I don't want the full turnaround. I want 90 less than that, and I want a negative angle, so I'll do 90 minus 360 to get a negative angle of 270 degrees. 315 degrees. I know this is 90, 180, 270, so 315 is somewhere between 270 and 360. At this stage, I don't care if it's accurate, it's in the correct quadrant, so close enough is good enough. 315 degrees positive rotation. Well, what is that in negative rotation? Well, if I subtract, right, starting here, and I go back 360 degrees, I'll end up at the same place. So 315 minus 360 is a negative 45 degree coterminal angle. We don't have to start with positive angles. We could also start with a negative 170 degrees or anything else. Negative 170 degrees. I know this will be negative 180. Positive 180. It's also negative 180. Negative 170 is not quite there, so I'm in quadrant 3. Now, since I have a negative angle to start, I want to add 360. I want to come back around full circle, so I'm going in the positive direction, add 360. Whereas here, I want to go backwards 360. So I go back 360 for a positive angle, I go forward or add 360 for a negative angle, and the coterminal would then be 190. One more in degree form, negative 210. Negative 210 is more, well, it's more negative than 180, so it goes past negative 180, but it is not yet to negative 270, so it's somewhere in quadrant 2. If I want a positive angle, I rotate in a counterclockwise direction, so I'm going to add 360 degrees to get back here again. 360 degrees plus a negative 210 makes a 150 degree coterminal angle. Alright, so now let's deal with these radians. 3 pi over 4. In my world, I think of this as 3/4. I know I have 0, half a pi, a full pi, 1.5 pi, and 2 pi. So I'm looking at 3/4 of pi. That's somewhere in between a half and 1. So I know I'm in quadrant 2. Now my positive angle is 3 pi over 4. I want to go back a full rotation, so I'm going to subtract 2 pi by getting a common denominator and then combining my numerators appropriately. This is the same as negative 5 pi over 4. For 2 pi over 3, positive rotation, I'll go back a full circle, so I'll subtract 2 pi. In common denominator, that's 2 pi over 3 minus 6 pi over 3. So my coterminal angle is negative 4 pi over 3. If I start with a negative angle, negative pi over 6, that's just a little bit down from our positive x-axis. I want a positive coterminal angle, so I rotate in the positive direction. I'll add 2 pi. 2 pi plus a negative pi over 6, that's 12 pi over 6 minus 11 pi over, minus 1 pi over 6, which gives us an answer of 11 pi over 6. So, if you're given a negative angle and you want a positive coterminal angle, you add 2 pi. If you're given a positive angle and you want to find a negative coterminal angle for whatever reason, you subtract 2 pi. It's always add or subtract 2 pi in order to find a coterminal angle. Alright, so we have other terms that you might remember from your childhood. 2 positive angles are complementary if their sum is pi over 2. 2 positive angles are supplementary if their sum is pi. And we could correspond that this is 90 degrees, this is 180 degrees. That's how we learn it in our younger days, but now that we're pre-calculus students, we use real numbers, we use radians. So complementary is pi over 2, which is 90 degrees. And supplementary, they'll add to pi, or 180 degrees. But this is key. I'm going to highlight it. 2 positive angles. So only positive angles can have a complement or a supplement. So let's look at an example, and I just put it in table form. It's a little easier than slide to slide to slide. If I'm given 30 degrees, I know that I need to add 60 degrees in order to get 90, so the complementary angle is 60 degrees. How far is 30 degrees from a total of 180 degrees? It's 150 degrees off, and so that's the supplement. So with degrees, for complement, we could do 90 minus the given angle, so in this case 50 degrees, which gives us a complement of 40. And for a supplement, 180 degrees minus the given angle, in this case 50, will give us a 130 degree supplementary angle. Keep in mind, if I have 110 degrees, what do I add to 110 to make 90? I add negative 20. But it has to be a positive angle, which means there's no complement to a given angle of 110 degrees. There is, however, a supplementary angle, so that's all good. Also in radians, pi over 4. Complementary angle, we'll do pi over 2 minus pi over 4, and 1/2 minus a quarter is a quarter. Supplementary angles, pi minus a quarter, that's 1 minus 1/4 is 3/4. 2 pi over 3, I do 1/2 minus 2/3, and then I realize, wait a minute, 2/3 is bigger. So this is already past 90 degrees. There is no complementary angle. There is, however, a supplementary angle of pi over 3 because 1 minus 2/3 is 1/3. Therefore, pi minus 2 pi over 3 is pi over 3. And for pi over 6, we'll subtract pi over 2 minus pi over 6 is the same as 2 pi over 6, right? This is 3 pi over 6 minus 1 pi over 6 is 2 pi over 6. The top of my pi kind of blew off. It's windy season here in New Mexico. And that simplifies to pi over 3. The supplement, pi minus pi over 6, 5 pi over 6. So it's, so far, coterminal angles. It's a matter of adding or subtracting 2 pi or 360 degrees, depending on what you're looking for. And complementary, the angles sum to be 90 degrees or pi over 2. Supplementary, the two angles add to be pi or 180 degrees. And I'm not sure I said that earlier one right, so let me say it again. Complementary angles add to be pi over 2, which is 90 degrees. Supplementary add to be pi or 180 degrees, but they have to always be positive angles. Alright. Now a second way to measure angles is through degrees, and we've kind of already talked about degrees a little bit. Degrees are a lot like percentages. They're things that we can visualize. But just like we don't do calculations with percentages, we change them to decimals, we don't do calculations with degrees very often. We use radians, which are real numbers. So a second way to measure angles is through degrees. Whole circle corresponds to 360 degrees. So a single degree is 1/360th of a circle. I can't even imagine trying to draw that for you. Also, 360 degrees is equal to 2 pi radians. So if this is true, we could divide both sides by 2. I'll get 180 degrees is equal to pi. And if I wanted to know a version of 1 to convert degrees to radians, we're going to multiply by pi radians over 180 degrees. Since pi is equal to 180 degrees, pi radians, this will be a form of 1. To convert the other way, multiply by 180 degrees over pi radians. So whatever you want your answer to be, that's what goes in the numerator. And whatever you're wanting to cancel, if you want to cancel the units of degrees, that's going to go in the denominator. Cancel radians, then the pi will go in the denominator. So let's convert a few of these. 315 degrees. Because I want to convert from degrees to radians, I'm going to put 180 degrees in the denominator. Pi goes in the numerator. We multiply our fractions straight across, and then when we divide, keep these ones in mind. When you're simplifying conversions, think about dividing by 30, 45, and 60. These are some of the most frequently used angles. In conversions, these will be nice factors that cancel out. And in this case, 45 goes into 184 times, 45 goes into 315 7 times, and I'll still have my pi. 240 degrees is 240 times pi over 180. 240 pi over 180. Once I reach this stage, I no longer have degrees. And 60 goes into 183 times, 60 goes into 244 times, so this is 4 pi over 3. What if we go the other way? Pi over 3 times 180 over pi. Notice how the pi's cancel out. I'm going to have 180 over 3, which is 60 degrees. 7 pi over 6. If you don't want to multiply straight across and you want to simplify first, I show you a method in this example. 7 pi over 6 times 180 over pi. I know 6 goes into 6 one time. I know 6 goes into 180 30 times. Pi's cancel out. 7 times 30 is 210 degrees. Just like time, degrees have subdivisions of minutes and seconds. There are 60 minutes, and we use a single apostrophe, so a tick mark, in 1 degree. And there are 60 seconds, which we use the little quotation mark, or a double tick mark, in 1 minute. Sometimes we use degrees, minutes, seconds, which is abbreviated DMS on calculators, and sometimes we use decimal degrees. It just depends. The most important thing to remember is parts of 60. Decimal degrees are in tenths, hundredths, and so on, using our base 10 numbering system. But degrees, minutes, seconds, the minutes and the seconds are parts of 60. So we're thinking more along the lines of time. 46.25. Well, if I told you it's going to be 46.25 hours, you would know it's 46 full hours, and 0.25 of an hour is 15 minutes. It's the exact same thing. So 46.25 degrees is 46 degrees, 15 minutes. 109.15 degrees. Well, the 109 is fine. We just have to take care of everything to the right of the decimal. 0.15 degrees is 0.15 of 60 minutes. 0.15 of 60 is 9. So 109.15 is 109 degrees, 9 minutes. 72 degrees, 39 minutes. Now I want to convert it to decimal degrees. The 72 degrees is no problem. The 39 minutes, that's 39 out of 60 degrees. 39 sixtieths is 0.65. So our decimal degree is 72.65. Negative 114 degrees, 19 minutes. Let's take care of that 19 minutes. That's 19 60th of a degree. And this is, repeating decimal. If I go to 2 decimal places, this will be a negative 114.32 degrees. Always round according to what your instructor or your homework system says. Arc length. There's a lot in section 4.1, this big introduction to trigonometry, so they're here and there and various. Stay with me, we're almost finished. For a circle of radius r, a central angle theta, and a central angle means inside angle, right? It's inside of the circle. It's at the center. Center. Central angle theta intercepts an arc length s given by s equals r theta, where theta is measured in radians. And this is nothing new, right? We defined theta to be s over r. Multiply both sides by r. Hey, look, it's radians. Seriously, though, you must use radians. Don't ever use degrees for arc length calculations, or you will be wrong. So let's see. A circle has a radius of 3 inches. I want to find the length of an arc intercepted by a central angle of 150 degrees. So I have my nice little coordinate system, and 150 degrees is about here. My radius is 3. Oh boy, look at that. I want to know this angle. What's this angle to get me to 150 degrees? I have no idea what that looks like, but not what I was trying to make it look like. So, first we're going to convert the 150 degrees to radians. That's 150 times pi over 180. 30 goes into both of these, and I end up with 5 pi over 6. Then I'm going to use the formula. The arc length is r times theta. I know the radius is 3. My theta is 5 pi over 6 in radians. And so my arc length is 5 pi over 2. If you're using WebAssign like we do here at UTEP, we're going to use the exact value. 5 pi over 2 is the answer. I don't care what your calculator says the decimal is, and neither does WebAssign. Give me an exact answer in these problems. So if a circle has a radius of 4 inches, I want to find the length of the arc intercepted by a central angle of 45 degrees. Let's see if I can draw this one any better. 45 degrees, that's better. If I'm at 4 inches for my radius, pretend I can hit that. I want to know the length of this arc, S. Well, I convert 45 degrees to radians, and that's pi over 4. That's one of those that you'll have memorized very soon. Then I use my formula, S equals r theta. R is 4, theta is pi over 4, so this arc length is pi. It's the length of pi. We can also use this formula to find a central angle. So a circle has a radius of 20 miles, maybe a search radius or something like that. Find the radian measure of the central angle intercepted by an arc length of 100 miles. The arc length, S, is 100. The radius is 20. When I divide, I get theta equals 5 radians. Keep in mind that radians don't always have to have a pi involved. Sometimes they're numbers that we're used to, like 5. 5 radians is a great answer. A circle has a radius of 125 kilometers. Find the radian measure of the central angle intercepted by an arc length of 1,000 kilometers. Well, arc length is 1,000. Radius is 125. I want to find theta, so I'm going to divide by 125, and theta is 8 radians. Do not overthink it. So let's consider a particle moving at a constant speed along a circular arc of radius r. Think about a dot on the outside of your tire on a bicycle, or the example I used in classroom was a circular saw, and we're looking at the tip of one of the cutting edges. If s is the length of the arc traveled in time t, then the linear speed v of the particle is v equals s over t, arc length divided by time. Moreover, if theta is an angle, always in radians, corresponding to the arc length s, then the angular speed, omega, of the particle is omega equals theta over t. There's another thing for us here. Trigonometry gets you to learn all sorts of Greek letters. So let's look at a carousel. A carousel with a 50-foot diameter makes 4 revolutions per minute. Side note, I lived in Broome County, New York, and that's the home of the carousels. If you're ever in the southern tier, check them out. They're all over the place. Just a little donation to the community is all it costs. Great carousels. Anyway, back to the story of math. We're going to find the angular speed of the carousel in radians per minute. Well, I know it makes 4 revolutions per minute. And 4 revolutions is a complete circle. 4 complete circles is 8 pi radians every minute. Notice how I already have my per minute, so it's already in the correct form for speed. Find the linear speed. So if I were to be on the edge and run this distance of the platform rim of the carousel, well, I know the diameter of the carousel is 50 feet. The radius is 25. So at 25 feet, going around 4 times, full circles, I would be going 200 pi feet per minute. I can guarantee you I cannot currently run that. Definitely. And finally, the area of a sector. Think of a sprinkler. It's watering a yard. Yes, sound effects. Added bonus to my lectures. For a circle of radius r, the area of a sector of a circle with central angle theta is given by a equals 1/2 r squared theta, where theta is measured in radians. But think about this. What's the formula for the area of a triangle in general? That's 1/2 base times height. Well, 1/2 r squared theta. 1/2, right, triangle. R, that's my base. R theta is my arc length, so it's almost like we're treating this arc length as the height of the triangle, but this isn't a triangle, right? This is an arc. I'm just relating it to a triangle. So if I want to find the area of the sector of the circle with radius r and central angle theta, where r equals 6 inches and theta is a pi over 3, my area is 1/2 r squared times theta. So I'll square r and get 36. And now I'll multiply. Half of 36 is 18. 18 pi over 3 gives me 6 pi square inches. Exact answer. I don't care what that decimal is. If the radius is 2.5 feet and theta is 225 degrees, the first thing we have to do is find the radian measure of 5 pi over 4. Convert to radians. 1/2 times 2.5 squared times 5 pi over 4. Well, 2.5 is fantastic, and when I square it, it's 6.25. And then I notice I have fraction, fraction, decimal in the middle. So I converted my decimal to a fraction. I know a lot of you would naturally convert the fractions to a decimal, but that gets a little tricky when I have pi, so I always go to fraction form. 6 in terms of fourths is 24, plus another quarter makes 25 fourths. Multiply my denominators, 2 times 4 is 8, 8 times 4 is 32. Multiply my numerators, 25 times 5 is 125 with the pi, and that is my final answer. So this was a not so quick, hopefully not too dirty, introduction to trigonometry, angle measurements, some of the terms that we used. Thank you for listening.